Hi, my name is Lily Donzeiser, and I'm an ASR senior at Darien High School. Today I'll be presenting on my project titled Evolutionary Responses to Climate Change in a Long-Distance Migratory Songbird, the Scarlet Tanager, otherwise known by its scientific name as Paringa olivacea. Starting off looking from the bigger picture, what is climate change? The majority of people use the terms climate change and global warming interchangeably. However, this is not the case, as global warming is only one aspect of climate change. Instead, climate change is composed of shifts in weather patterns, such as more major weather events, rising temperatures, sea levels, and more. Such changes are catalyzed by the steady increase in greenhouse gas emissions, and having more of these gases consequently intensifies the greenhouse gas effect, the process by which the Earth is warmed. This round of climate change, because of humans, is occurring at such a fast pace that has never been seen before. As a result, today we're living through the sixth mass extinction, as many species are not able to keep up with the fast-paced climate change. So, when climate change is put into contrast with evolution, we can see that evolution is a very slow process while climate change is very fast. Evolution requires time in which natural selection can take place as the species that are most fit to live in a given environment are selected to reproduce and pass on those beneficial traits. Many species have adapted to live in certain environments as a result, but now that climate change is changing these conditions and rapidly, this poses a threat to the process of evolution and forces species to attempt to adapt or to become threatened with extinction. In this study, the scarlet tanager was chosen as the focus species to track how climate change is impacting species evolution. The scarlet tanager is a migratory species, meaning that they travel to the more northern regions of North America in the summer months to carry out their breeding cycles. For their breeding to occur and for them to exist in their summer locations, certain conditions are necessary. However, when conditions start to change, the scarlet tanager may become vulnerable to natural selection if they're not able to evolutionarily adapt at an equal pace with climate change, or they rather might have a low vulnerability if conditions become more favorable under future change. This begs the question, does the scarlet tanager have adaptive potential to adjust to climate change? This study focuses on looking for such adaptive potential in breeding range shifts, as well as morphologically in their physical appearance. So similarly to the previous question, the problem statement for this experiment is how is climate change affecting the breeding range distribution and morphological evolution of Paringa olivacea, and does the species exhibit adaptive potential under future change? Essentially, are we going to see a change in the location of the scarlet tanager in North America during their summer breeding period, and will we see physical evolutionary adaptations that help demonstrate the species' vulnerability? The study hypothesized that the Paringa olivacea will show minor signs of a shifting breeding range and morphological alterations as an indicator of adaptive potential, but under future change, the species will ultimately prove to have a high vulnerability to climate change. I came upon this hypothesis in particular due to the species' status as a migratory species, meaning that they require very specific environmental conditions and physical attributes to live in its summer regions, and when climate change threatens both of these factors, it will put the scarlet tanager at high risk. Additionally, because historically the scarlet tanager tends to favor cooler breeding ranges, I hypothesize that rising temperatures will highlight further the vulnerability of the species under climate change. To analyze such adaptive potential in the scarlet tanager, the use of species distribution models, otherwise known as SDMs, was employed, specifically the use of MaxEnt, a model developed by the American Museum of Natural History. The MaxEnt model has a strong scientific reputation and was recommended to me by my mentor, Dr. Maggie McPherson. In simple terms, what MaxEnt does is it uses climatic grids, so what environmental conditions look like in a given area, and pairs them with occurrence localities, so where a species was seen. This breeds an output that shows the predicted suitability of a species in a given region, and what environmental variables used in the program were the ones that contributed most to a species' suitability. Locality data in the study was used from GBIF from the years 2000 to 2020, and the climatic data was used from WorldClim. The environmental variables being analyzed in this study are minimum temperature, maximum temperature, and precipitation. Future projection models were additionally created using current locality data combined with environmental data by WorldClim under scenario RCP 8.5, which is the business as usual for the emission scenario, and was also projected to the year 2070. As to the morphological analysis aspect of this project, morphological data belonging to the scarlet tanager was obtained from Louisiana State University Museum of Natural Sciences, where my mentor is currently employed as a postdoctorate researcher. Our species samples range from 1887 as the oldest to 2017 as the youngest, in order to track the full progression of climate change along with physical differences, and about 30 specimens in total were measured. Measurements were taken on a caliper, as seen in the bottom photo there, and a handful of measurements were taken, some of which included bill length, bill width, bill depth, tarsus, tail length, and more. The morphological results were analyzed using linear regression in Excel. Though it was mentioned that multiple morphological characteristics were collected and measured, the only result that yielded a significant difference, with the p-value of 0.034%, was the pattern in tail length. On this graph, the y-axis is indicative of tail length in millimeters, while on the x-axis is the year in which the bird specimen was preserved. At the earliest data point, 1887, the tail length was 3.11 millimeters, and in 2017, it was at 3.31 millimeters. Though there are some outliers, this graph shows a clear increase in the slope upwards of the trend line when it comes to the tail length in the scarlet tanager over time. Though there were results on MaxEnt for the months of April through October, these are some of the most significant results. First, we have the August MaxEnt models. Seen in the table, minimum temperature was the environmental variable that contributed most strongly to the presence of a scarlet tanager in a given region, so at 85.5% contribution and 93.2% permutation importance. So when predicted suitability on these maps is shown as high, it is because minimum temperature is high in the region and restricting the species to that location. For the models themselves, on the left we have under current conditions, and on the right under future conditions. Please keep in mind that the warmer the color, so the more closer to red that the colors are on the map, the more suitable the species is to that given region. On the current model, it is apparent the species range stretches north but is more confined, while the future 2070 map shows a huge range shift up into Canada and a much higher suitability in the north as temperatures continue to rise. In the same layout as the past slide, the October results are also significant. Again, minimum temperature was the most significant environmental variable. Even though maximum temperature has the highest percent contribution, its permutation importance is 0, meaning that when it was removed from the model altogether, the model did not change at all, showing minimum temperature to be the most significant environmental variable over maximum temperature instead. The current model on the left shows the species beginning to migrate back down south as conditions are warmer there, since again, minimum temperature is what is controlling the range, specifically around the Gulf of Mexico, where it is visible that the warm red color indicates high suitability in those regions. Under the future model, however, the range of the scarlet tanager covers nearly the entire continent of North America, even stretching into Alaska, a huge change from the current October model seen on the left. Moving on to the discussion of the results, specifically that of the morphological analysis, it was found that the tail length had significantly increased. Tail length increases can be correlated with the need for longer travel, as longer tails help accommodate for more efficient flight by creating lift, a force that keeps the species in the air due to the difference in air pressure that is created as wind flows by. This means that the scarlet tanager has a lower vulnerability than previously assumed, as these morphological findings demonstrate that the scarlet tanager may in fact be adapting in time to climate change, and demonstrating a high adaptive potential, whereas the hypothesis claimed that the species would show minor signs of any physical evolution and have low adaptive potential. As for the discussion of the MaxEnt results across the board for all the species distribution models for the months of April through October, minimum temperature was the most significant environmental variable in 4 out of 7 months. This means that species favor warmer conditions, so higher temperatures under future change are actually more favorable by the scarlet tanager. As a result, the species demonstrated a high potential for a breeding range shift in future conditions, as models such as the August ones pointed out, as temperatures rise in historically colder regions up north. Findings in the October model even brought up another question, the migratory status of the species. The October model, in a month where the species is beginning to shift back to Southern American regions, predicted that the species would have an expansive range all across North America in correlation with rising temperatures. This poses the question, does the scarlet tanager need to remain a migratory species if conditions become more favorable year-round? And will the species become sedentary just as the American robin has recently done? Again, the hypothesis for the MaxEnt models was disproved as the results instead show that the breeding ranges were becoming more extensive under future chains instead of smaller, demonstrating a rather high adaptive potential. The sources of this error in the study can be separated into 2 categories, that for morphological analysis and the distribution modeling process. As for the morphological analysis, the biggest source of error could be my personal newness to techniques and the use of the caliper to take measurements, though I was properly trained and checked by my mentor as well beforehand. As for distribution modeling, the models do not account for the possible migratory to sedentary switch discussed previously, but more largely it also does not account for competitive exclusion, which could arise between the scarlet tanagers shifting into new regions and having to compete for resources with existing species. Again, the reliance on outside sources for both locality data and environmental data is a potential source of error. Though both databases are reliable, there is always that potential room for error. As for the implications of the study, these findings can be employed in conservational fields as the results can help conservationists determine which species to focus on first. Since the findings of the study demonstrated the scarlet tanager to have all right, to have high adaptive potential, this can push conservationists to focus on more endangered species. Even economically, the study can help determine the specific habitats we need to preserve in order to allow a species the chance to adapt to future change. Because if we focus on protecting these habitats, we can not only preserve species, but continue to enjoy the economical and ecosystem services that they provide us. In total, for future work on this project, I'll be focusing on writing my final paper and also becoming a published author alongside my mentor as we aim to write and co-author a journal article together on these findings. Additionally, I may have a potential presentation at the American Ornithological Society in the summer, where I would be presenting my findings in the study to a national audience. As for the community's future work, it is my hope that this study and its methods can be applied to other birds and even other species to determine other species' vulnerability to climate change, as well as highlight the increasing relevance of SDMs in the scientific community. And most importantly, it is my hope that this study will be added to growing collections of literature and be applied to conservation efforts that determine which species need our help the most, so we can all take immediate action to protect our planet's species. Are there any questions?